Welcome to my video presentation of the paper Analytical Solution for the Cost-Optimal Electric Energy Storage Size based on the Effective Energy Shift algorithm. My name is Fellerer and I'm presenting this presentation, which has been accompanied by a publication in the lecture notes for computer science in the Springer Energy Informatics proceeding. It was presented at the EnergyInformatics.Academy 2024, which happened on Bali at the October 24th. My topic revolves around decentralized energy grids and more specifically microgrids, which are one of the key technologies that will hopefully help mitigate effects happening in the transition to more renewable energy sources and a more sustainable energy provision. Infrastructure microgrids are typically constructed out of three different components. Obviously, you have some energy demand or electricity demand. You have some source of generation. Most households probably have, at least in Germany, some photovoltaic panels on the roof, so it's a renewable energy source, but it could also obviously be a generator, diesel generator or similar. A microgrid can as well have an electric energy storage system, short and abbreviated by EES, and it can or might not be connected to an energy market and a grid. And microgrids can either be isolated, so standalone, or grid connected. Obviously, in those kind of microgrids, you have a lot of technical components, and as usual, the cost arises how large, so what should be the optimal size of the different components. For example, how many photovoltaic panels should you place onto your roof, or how much energy storage should you actually buy for your house? On the bottom left, you can see a really simplified, nevertheless somewhat accurate representation about the investment costs or the costs overall for different system sizes. Typically, investment costs, so just the buy-in prices for systems increase with an increasing size, hence here this red linear line. The dashed blue line indicates a reduction in the operating costs. You can see here it stagnates at one point because the avoided costs provided by a larger system at one point stagnate. So operational maintenance costs might still increase, but the avoided costs, so how much energy you have to buy and sell from the grid, for example, is limited by the other components in your microgrid. The black line now shows the total costs of basically ownership. So it includes investments, maintenance, operation, and buying, selling, exporting energy to the grid and buying it from the grid. And here you can see there is actually an optimal size. There might be multiple ones, obviously, but there is at least one optimal size which reduces your overall costs of ownership. In my publication, I used a single family house as a use case since it's quite prevalent and heavily discussed topic right now, at least in Germany and also worldwide. And here the reference system looks like a traditional house. So you only have energy demand, here abbreviated by capital E, DEM. You have to import all of the energy by the market for some import price, lowercase p imp, and this will produce obviously some costs. So here costs are lowercase c and then ref for the reference costs. That's the base use case, basically. Not really a microgrid yet, but once we add a photovoltaic panel to the roof, for example, we can now actually generate or produce energy. So here, energy generation, so gen for generation. And this one might be able to cover your demand. Hence, at some points, you might be interested in exporting this energy, so selling it to the grid, sometimes also called to feed it in, for a price P exp. So here export, exp for export. This will also save you some energy to import, because now you're producing your own energy in your system boundaries. Hence, you get a change in your overall costs of ownership of your house by C0. So C0 here includes investment costs into your photovoltaic system, savings by a reduced energy import, and additional revenue by exporting energy. Obviously, C0 here can be positive, so you might have to pay more in the end. So it would be, from cost perspective, more optimal to not invest into a photovoltaic system at all. But in most cases, C0 here is actually negative. So negative costs, which means you are saving money. That's actually with the current and future photovoltaic cell costs per square meter, for example, and the price for energy at the market, almost guaranteed. Like obviously for some system sizes or systems it might vary, but for a single family house you basically never pay on top. The next extension of our microgrid is to install a battery storage system. So some lithium-ion batteries, for example. And here you can now store energy from your generation and use it later, at a later point in time, to cover your demand. This additional energy that you can get from your battery storage system is here abbreviated as capital E plus. And similar to the photovoltaic system, it decreases now the energy that you can export, because you are able to store it now internally. But it also decreases the energy amount that you have to import, because you were able to use more of the generated energy internally. Hence, again, we have a change in our total cost of ownership, C+. The most prevalent method found in the literature up to date to analyze and size microgrids is by the means of simulation and optimization. It's not really surprising, because it's flexible and adaptable to specific use case. You can handle quite complex and nonlinear system dynamics as, for example, temperature dependent efficiencies in charging and discharging, battery aging, photovoltaic aging, and many more complex systems. That's why it's so useful, and yeah, you can be used to analyze completely new system configurations that are not even built or existent. They come with a big caveat, however. They are quite complex to set up and to configure. Simulations have potentially very long run times, even though there are simulation models that obviously run quite fast, but since you basically always have to do some kind of parameter variation to get some decent statistics on your system behavior and in your sensitivity, the overall run times are usually quite long. And the last point here is that simulations and results published based on simulation models are typically quite hard to reproduce. The source code is either not available, the models are not available, or the original data has not been published. That brings me to the question of my paper. Does a closed form expression for the cost optimal usable capacity of an EES within a microgrid exist? And can we derive this closed form solution from analytical methods, so without relying on simulation? A big important role here plays the effective energy shift algorithm. It's an algorithm developed by myself in a previous publication, which is currently, to the date of the presentation and the conference and this recording, under review for the Applied Energy Journal. It's relatively easy to use, available online on my GitHub page, where the link you can see here on the slide. A preprint version is available as well via the preprint archive SSRN. And here on the bottom you can see the title. The effective energy shift algorithm is an analytical method based on a linear model, and it uses time series for generation and demand, which you can see here on the right. So on the right side, E-gen here is on top of a graph for a typical photovoltaic curve. So you can see the peaks during the midday hours. And on the right side, you can see a demand. In this case here, it was a demand for a 4-person single family house, standalone in the middle of Germany. But it doesn't really matter which time series you take, since in this case here, the algorithm is agnostic. Additionally, it can take into account constant coefficients for efficiencies. In this case here, du is for the direct usage from generation to demand. Ch stands for charging. So here eta Ch is the charging efficiency of our storage system. And dCh obviously stands for discharging. On top of that, in this current publication, included are an efficiency for exporting energy and an efficiency for importing. In many systems, those are most likely one, at least the eta for import, but eta for export. So if you want to export, for example, from your generation, from your PV to the market, there's at least one inverter in between, which has its internal efficiency metrics. And important for this presentation here, those efficiencies are mean values. So if you have a varying mean based on some function or nonlinear relationship, you have to construct the mean value for your system. So typically run it for a really long runtime until it reaches steady state, cut transient state effects, and then calculate your mean value out of it. The effective energy shift algorithm assumes a specific pattern in energy usage, which is the first you use energy generated in your system directly. So you directly cover your demand by your generation. Second priority is anything that's left over, you try to store. You try to charge your battery, or you try to discharge if you still have demand left over. And only as the last resort, you sell and buy any remaining excess or deficit to the market. One big additional condition here is that no energy is sold or bought for the EES, for the energy storage system. So you don't charge your battery with electricity that you imported, and you don't sell energy that you stored inside your battery system. I'm aware that there are use cases and business cases where you have your battery system also participating in the market. Business cases where you just use your battery model for flexibility purposes. So the energy amounts are not that high, but you and average out more or less. In those cases, this model here and this analytical method might still be applicable. However, if you primarily use your energy storage for trading, then this method here doesn't work because it violates the big assumption of the EfES algorithm. I've shown that the EfES algorithm computes extremely fast and it scales well with a operational complexity of n. So there is no iteration involved. It's not an approximation. It's an analytical, precise solution for this linear model. What does it provide us with? It provides us mainly with the additional energy, E+, now as a function of the capacity of our storage system, so capital C. And it provides us with the derivative of our additional energy with regards to the capacity. And this one I called local effectiveness. So effectiveness is a term coined by myself in the publication for the EfES algorithm. And it's a measure on the operational performance. The additional energy curve, so E plus of C, is continuous, it's increasing, and it's piecewise linear. So it's defined by two different arrays, so here E plus and C in bolder font, and you can see here on the right side that's the result for our single family house. It actually looks like an exponential distribution here on the right side, but once you take a closer look and zoom in, so here in this red box, you can see that it actually is constructed out of piecewise linear functions, so straight lines between dots. Once you look at the derivative of our E+, so at the local effectiveness, you can see that it actually is a decreasing and piecewise constant step function, defined again by the same C array, the C vector, so which defines the points where your steps actually go down, and M defines the height of the stairs. Based on our function E plus of C, so the additional energy, we can now calculate and construct a function for the overall costs of ownership C. So lowercase c of capital C. Costs as a function of the capacity of our EES. On the right side in gray, I marked and I printed and plotted the important values and metrics and the final curve that is constructed. In the left axis, you can see our reference cost, CREF, here at approximately 1.25 thousand euros approximately. So that's where our house started without having any photovoltaic. Once it installed photovoltaic system, it saved money. So here C0 here caused the Y offset to go down. And now our overall cost function here provides us with the bold gray line. All investment costs for the EES are calculated with the price per usable capacity. So abbreviated here with lowercase p, inv for invest and EES for the EES. On the bottom right, you can see the overall function. So it has the initial offset CREF minus C0 and now a term depending on the capacity. On the right side, you have the investment costs, so P inf EES times C, which is at the moment roughly 700 euros per kilowatt hour for lithium-ion batteries. Sometimes they go down to 500, sometimes they are still more expensive. And on the left side, you can see the price for the additional energy. This one here is now dependent on import prices, export prices, efficiencies, etc. If we want to find the minimum of our cost function, we are interested in the derivative of our cost function to find the root for our derivative and therefore our cost optimal capacity. We have to find the capacity that satisfies the following inequality, so where our derivative goes from negative to positive, which means at which point do our overall costs go up again when we increase our battery capacity. If no solution exists, then the optimal capacity is 0. So that means it's better to not own any battery storage or energy storage at all. On the right side, you can see the derivative in gray, now in the same plot as our local effectiveness M. And the green line here indicates where our derivative of our cost function actually changes the sign. You can reformulate it to just having to look for an local effectiveness value. How do we calculate our M star, which is the cost optimal local effectiveness? It's this small little fraction here. On the upper part, we have our investment costs for the EES times charging and import efficiencies, and on the lower side, we have the difference from import to export, where the import price has to be scaled by charging and discharging efficiencies, and the export price has to be scaled with the import and export efficiency. So we calculate our M star, and then we have to find the index in our local effectiveness arrow. Once we find our index in our decreasing local effectiveness array, we already have our cost optimal capacity. Obviously, there are some limitations to this algorithm. The main one comes from the linear model with constant parameters that is used. Sometimes constant parameters are hard to come by, sometimes they are not. Most of the time, system parameters in technical sheets are actually reported as constant parameters because many providers don't want to hassle with curves. Hence, just looking in your technical data sheet might already provide you with a constant parameters that you could use. If you only have access to curves or you want to look at it in a more detailed manner, then you have to most likely use numerical methods, so simulation, for example, to get a good estimate on your expected performance efficiency, so on your average. And another limitation comes from the EfES algorithm itself, since it uses the patterns arising from the greedy control algorithm for the EES. So first use direct usage, then usage of the battery storage, and lastly importing and exporting to the grid. This greedy strategy, however, is also quite common in households because it's easy to implement on the system itself. So this pattern that the EfES algorithm exploits in here is quite prevalent right now. I don't know if it's still the same operational methods in 10, 20 years, but for current system, that's definitely an important pattern that arises. To summarize the results, it was possible for me to come up with the analytical derived closed form expression for the cost optimal usable capacity of a storage system within microgrids. Since the EfES algorithm scales well and the calculations presented in this paper here basically have no computational impact, we can say that finding the solution is also just a matter of linear complexity. It's extremely fast to compute. I published everything, so also the source code for this publication, on my GitHub page. Here you can see the link for the data I used and the source code you can find online. And obviously, once you calculate the cost optimal capacity based on this expression here and the algorithm, you don't have to stop here. Yeah, look, you can still use it for more complex studies. So if you want to have an optimizer run on your physically more precise system, they still need initial values. So why don't you just get a really good estimate based on a linear model out of this equation and use it in your optimization problem that you might be interested in solve it. Or obviously, especially if you look at the planning studies for communities or for regions, most of the time they are fine with just rough dimensionings, rough guesses, educated guesses basically. And those kind of rough dimensionings can obviously also already be achieved with a linear model. Thank you very much, and I hope for an interesting discussion in the YouTube comments if they are enabled. You can also contact me directly if you need more information or you want to collaborate, or just write me a post on my GitHub page. I will also see this one.